Now, in a previous video, we defined what a definite integral was, and we went through some properties of definite integrals. In this video, we're going to use the fundamental theorem of calculus to evaluate a definite integral. Now, what this theorem basically says is that I can evaluate a definite integral. So I'm going to integrate on the interval from a to b, and then evaluate that by replacing in my antiderivative everywhere I see a variable. I'm going to replace it with my upper limit of integration, so this value here. And then I'm going to also plug in the lower limit of integration everywhere I see an x in my antiderivative. And then I'm going to find the difference between those two values. So it's always f of the upper limit of integration minus f of the lower limit of integration. So let's take a look at an example and see how that works. So here I've got a fairly simple integrand. So I'm going to start by integrating using whatever techniques of integration that I need to use. And in this case, I'm just going to need my power rule and my constant rule. So let's start by integrating. So I'm going to get an antiderivative that looks like this. I'm going to take my coefficient divided by my exponent plus 1 minus coefficient over exponent plus 1, and then for my constant rule, I take the constant and multiply by my variable, so I just get x. So if we clean that up just a little bit, I've got x to the fourth minus 2x squared plus x. Now, once you integrate, we're going to add in a little bit of a new notation here, because what we want to do is evaluate this antiderivative for these limits of integration. So the notation to show that I'm going to do that is you draw this short vertical line segment and you put your limits of integration there. So this is essentially saying that I'm going to evaluate x to the fourth minus 2x squared plus x from -1 to 1. Now, the fundamental theorem of calculus says that I start by replacing in that antiderivative the upper limit of integration, the 1, and I'm going to subtract from that what I get when I replace all of those variables with -1. So from here on out, it's substitution and arithmetic. So let's go through and see what this looks like. So if I replace in my 1 everywhere I see an x, I'm going to have 1 to the fourth power minus 1 squared plus 1. And then I want to subtract from that, replacing all of those x's with -1. So I'm going to have -1 to the fourth minus 2 times -1 squared plus -1. And now I just want to evaluate all of this. So in the first set of brackets, I've got 1 minus 2 plus 1, or that looks like 0, minus, if I evaluate it over here, I get -1 to the fourth is +1, -1 squared is +1 times -2, and then plus another -1. So here I get -2. And finishing out the arithmetic, then 0 minus a -2 is equal to 2. So evaluating that definite integral gives me a value of 2. Now let's take a look at another example. So here I want to evaluate the definite integral of 2x squared times the quantity x cubed minus 5 to the fourth power. So I know when I see a sum or a difference raised to a fairly large power that I'm going to use integration by substitution. So let's start working through that process. So remember, the first thing that I want to do is define my u. So when I have a quantity to a large power, u is going to be that quantity inside the parentheses. So I'm going to let u be x cubed minus 5. Then I find the derivative of that. So du is equal to 3x squared dx. Now the next step is to see if I have what I need, if my derivative is present in my integrand. So what I need in my integrand is a 3x squared dx. But what I have in my integrand is a 2x squared dx. So I only differ by a constant. I need that 2 to become a 3, and that's something that I can fix. So I'm going to rewrite this integral as the integral from 0 to 1 of 3x squared times x cubed minus 5 to the 4th power dx. Now remember, I need a constant out in front of that integral that takes that 3, divides that 3 back out, and multiplies back in the 2, so that this is still equivalent to the original problem. So out in front of my integral, I need to divide out that 3 that I put in there and multiply back in the 2 that I took out. So here's what I want to integrate. So now I'm going to make my substitution. So my new integral, after I substitute, will look like this. I'll have my 2/3 out in front of my integral symbol, and I'm going to replace my u for the x cubed minus 5. So I'm going to have u to the 4th power, and my 3x squared dx is now du. So I want to integrate u to the 4th, and I want to multiply by 2/3 in the end. Now, I didn't put any limits of integration on here because I need to talk about how those limits are affected by this substitution. In the original problem here, I had limits of integration from 0 to 1. Now, those limits of integration were x's. X equaled 1, x equaled 0. That was what my integral was with respect to. But notice now, my integral doesn't contain x's. My integrand contains u's. So that means that I don't want to have limits of integration that are x's. I need limits of integration that are u's. So I need to take a minute over here and figure out what my, oops, I don't want flat, figure out what my new limits of integration are. So let's start with that lower integration of x equal to 0. So for x equal to 0, what I want to figure out is what is u. And we've got a formula right here that will allow us to find a u for any given x. So all I'm going to do is in this u, I'm going to replace that x with 0 to find out that my new lower limit of integration should be -5. Then I'm going to do that same thing for the upper integration value of 1, or the upper limit of integration, x equal to 1. So if I plug that into that formula for u, I've got 1 cubed minus 5, which gives me -4. So that means back over here in my new integration, I'm going to be integrating from -5 to -4. Now my limits of integration are u values instead of x values. Okay, so let's finish out the problem. The next thing that I need to do is to integrate. So I'm going to have this 2/3 still with me, and I want to integrate my u to the 4th du. So I've got coefficient over exponent plus 1, exponent plus 1. And if I multiply that 2/3 by the 1/5, I get 2 over 15, u to the 5th. And remember that I want to evaluate that with my new limits of integration, -5 to -4. So now it's a matter of substituting and doing my arithmetic. So using fundamental theorem of calculus, I want to figure out what f of, for f of u, let's do that, f of -4 minus f of -5. So if I replace all of those u's with -4, I'm going to have 2/15 times, times -4 raised to the 5th power minus 2/15 times -5 raised to the 5th power. So replacing my -4, my upper limit of integration, then replacing my -5 as my lower limit of integration. So getting on my calculator and doing this arithmetic, this first value works out to be -136.53. We round to the nearest hundredth. And the second value turns out to be -416.67. And so if I do that final arithmetic, I get an overall value of 280.14.